The year 1997 stands as a pivotal moment in the history of physics. It was a year of intense intellectual ferment, witnessing the culmination and consolidation of a revolutionary paradigm shift, the birth of quantum mechanics. Central to this seismic change was Niels Bohr's contribution, specifically his paper, The Quantum Postulate and the Recent Development of Atomic Theory. This work, presented at the CMO conference, represented a profound articulation of the Copenhagen interpretation, laying the conceptual groundwork for understanding the bizarre and counterintuitive world of the atom. It was a paper that both synthesized existing ideas and proposed radically new ones, offering a coherent framework where the seemingly contradictory wave and particle natures of matter could coexist. The intellectual landscape preceding Bohr's 1927 work was one of both triumph and turmoil. The Rutherford model of the atom, proposed in 1911, had successfully replaced the plum pudding model, postulating a dense, positively charged nucleus surrounded by orbiting electrons. Yet, this model presented a significant problem. According to classical electromagnetic theory, orbiting electrons should continuously emit radiation, losing energy and spiraling into the nucleus, rendering the atom unstable. This presented a direct conflict with the observed stability of atoms, a fundamental property of matter. The genesis of quantum theory began to address this problem. Bohr, in his seminal 1913 paper, On the Constitution of Atoms and Molecules, tackled this issue by incorporating Max Planck's quantum hypothesis, first proposed in 1900. Planck theorized that energy, particularly electromagnetic radiation, was emitted and absorbed in discrete packets, or quanta, with energy proportional to frequency, given by E equals h times f, where E represents energy, h represents Planck's constant, and f represents frequency. Bohr, building upon this, postulated that electrons could only occupy certain discrete orbits or energy levels around the nucleus. These orbits, characterized by specific quantized energy values, were stable. An electron could jump between these orbits by absorbing or emitting energy in the form of quanta of radiation, with the energy difference between the levels precisely matching the energy of the emitted or absorbed photon. This model successfully explained the line spectra of hydrogen, a triumph of theoretical physics. However, the Bohr model, while revolutionary, was still a hybrid, combining classical mechanics with quantum conditions in an ad hoc manner. The underlying mechanisms for the quantization rules remained unexplained. The development of quantum mechanics in the years leading up to 1927 witnessed a flurry of theoretical breakthroughs, each adding crucial pieces to the puzzle. Werner Heisenberg's formulation of matrix mechanics and Erwin Schrödinger's wave mechanics offered alternative, yet mathematically equivalent, descriptions of quantum phenomena. Heisenberg's uncertainty principle, formulated that same year, established a fundamental limit to the precision with which certain pairs of physical properties of a particle, such as position and momentum, can be known. This was a concept so counterintuitive, it initially sent shivers down the spines of even the most seasoned mathematicians. Schrödinger's wave equation described the evolution of quantum mechanical systems, and Max Born's probability interpretation of the wave function introduced the idea that the square of the wave function gives the probability density of finding a particle at a given point in space. These concepts, although distinct in their mathematical formulation, provided tools for calculating the behavior of quantum systems. These differing frameworks, however, required a cohesive interpretation. Bohr's paper, presented at the CMO conference, provided this critical interpretation. The core of his work lay in the articulation of the quantum postulate. Bohr proposed that the quantum postulate should be considered a fundamental principle that applied to all atomic processes. This postulate, in essence, stated that the description of atomic phenomena requires a specific limitation of the classical physical laws. It acknowledged that classical concepts, such as position and momentum, could be used to describe quantum systems, but only with certain restrictions, dictated by the quantum of action, Planck's constant. Complementarity, a central theme in Bohr's interpretation, stated that certain properties, such as wave-particle duality, were actually complementary aspects of the same physical reality. Bohr maintained that an experiment designed to reveal the wave-like nature of a particle would necessarily preclude a precise determination of its particle-like properties, and vice versa. This was a fundamental departure from classical physics, where a complete description of a system was, in principle, always possible. Bohr's paper also addressed the methodological challenges of applying quantum mechanics. The paper was not merely theoretical, it provided a framework for navigating the complexities of quantum phenomena. Using the concept of complementarity, Bohr proposed a method for making quantum mechanics work. This framework used classical descriptions as a foundation and applied quantum principles to these classical images. Bohr's approach provided a consistent framework for understanding the results that came from Heisenberg's and Schrödinger's mathematical formulations, the impact of Bohr's work was immediate and profound. It clarified and unified the various, seemingly disparate, formulations of quantum mechanics, transforming it from a collection of mathematical tools into a coherent and logically consistent theory. It offered a philosophical underpinning for the quantum world, which directly led to the general acceptance of the Copenhagen interpretation. This interpretation, which provided an interpretive framework for understanding quantum mechanics, quickly became the dominant view amongst theoretical physicists. It offered a clear path for interpreting the results of quantum experiments. The 1927 Comeau paper also sparked immediate and ongoing debates among physicists concerning the validity and implications of its postulates. The most prominent critics from this period include Albert Einstein, who, despite his own contributions to the development of quantum theory, never fully accepted the Copenhagen interpretation. He expressed skepticism about the probabilistic nature of quantum mechanics, famously stating God does not play dice. Einstein favored a deterministic view of reality, as opposed to the probabilistic interpretation that was central to Bohr's model. The debate between Bohr and Einstein, carried on through numerous discussions and thought experiments, shaped the evolution of quantum mechanics, encouraging a deeper exploration of its foundations. The legacy of Bohr's quantum postulate and the subsequent development of atomic theory remains significant. The concepts outlined in his paper have become fundamental to our understanding of the physical world. The quantum postulate is crucial to the technology in our everyday lives. Quantum mechanics, as interpreted through Bohr's framework, is the foundation of nearly every single modern technology, from lasers and transistors to medical imaging and nuclear energy. His ideas continue to inspire physicists to understand the deeper foundations and implications of quantum mechanics. The concept of complementarity, which he introduced, has found applications beyond physics, influencing fields like philosophy, psychology, and even the direct influences on Bohr's work were numerous and came from diverse sources. The initial inspiration came from Planck's quantum of action, coupled with Einstein's explanation of the photoelectric effect, using the concept of light quanta. From this, Bohr formulated a model for the atom, which was then developed by Heisenberg, Schrödinger, and Born. These scientists provided him with mathematically more rigorous and detailed formulations of quantum mechanics. Heisenberg's uncertainty principle and Schrödinger's wave equation both reinforced Bohr's ideas by providing a solid mathematical basis. Bohr's work, in turn, had a profound impact on numerous subsequent developments. The Copenhagen interpretation, as developed by Bohr and Heisenberg, served as a foundation for nearly all of the subsequent theoretical and experimental advances in quantum physics. The work of Paul Dirac, who developed a relativistic quantum theory, built upon Bohr's ideas, as did the later works of Wolfgang Pauli, who pioneered the study of the fundamental particles and discovered the Pauli exclusion principle. These works developed quantum mechanics as a discipline. In conclusion, the quantum postulate and the recent development of atomic theory presented at the Comeau Conference in 1927 represents a pivotal moment in the history of science. Through his concise yet comprehensive articulation of the quantum postulate, Bohr provided the conceptual framework for understanding the quantum world. This work served to unify the existing theories and interpretations of quantum mechanics. It also provided a clear and concise paradigm shift within the theory. Bohr's legacy extends beyond the realm of physics, sparking fundamental questions about the nature of reality and influencing a multitude of disparate fields. His profound insights, articulated with intellectual rigor and clarity, have left an undeniable mark on the landscape of scientific thought, ensuring his place as one of the most influential figures of the 20th century. The quantum revolution, a legacy of profound intellectual change, continues to resonate today, a testament to the enduring power of his vision